Okay, today we're going to talk about 7.2b. We're going to continue talking about volumes of solids of revolution. And we've been talking about volume of solids of revolution the last couple days. But all of the volumes that we found, when we found them, we've sliced our little figure into little cylinder shapes or even washer shapes. But when we've sliced them so that they were circular, right? They were either a circular disc or a circular washer, a disc with a hole in it. Today we're going to talk about what happens when we slice our shapes and they're not circles anymore. Okay, maybe they're squares or triangles or something like that. Part of your homework tonight is on page 463 and it's numbers 1 through 10. What I'd like you to do on these problems is I'd like you to set up the problem, set up the integral, and then just evaluate it using your calculator. Okay, but I would like to see a setup and then you can just plug it in your calculator and evaluate. Okay, so let's start talking about volumes of solids with known cross sections, it's called. And so we've been talking about volumes of solids of revolution where their cross sections are circular. For example, if you look at a figure that looks like this, when we slice this little figure, it ends up being a little circular cylinder type of shape, right? And if we wanted to find the volume of this shape, we would take our little cylinder shapes, we would take the area of it, pi r squared h, and we want to find the volume, so we integrate it. Oops, pi r squared h. We integrate it. This little h changes to a dx, and then we're really just integrating. What does that look like? Pi r squared. Isn't that the area of a circle? Right? But in this case, it's a three-dimensional circle or a cylinder. Okay? So that's kind of what we're going to be doing today, but instead of circles now, they're going to be shapes maybe that look like this. Okay? So if we end up slicing this little shape in order to find its volume, their shapes, their little slices, aren't going to be little cylinders or washers anymore. They're going to be more like square shapes. So maybe like a little square-shaped prism. Right? And so how do I find the area of a square-shaped prism? Well, I take the area of the base, which is a square, base times height, and since it's a square they're both the same, can I say x squared, times the little heights or the little widths of my little square shapes, and if I'm finding an infinite amount, I'm going to integrate it, right? And so what I'm really doing is I'm integrating the area of a square. Okay, so what happens then if my slices, let's say, are little triangular shapes? Right? If the slices are little triangular shapes, they're going to be little triangular shapes prisms. What's the area of a triangle? Base times height divided by 2 times my little widths of my triangles. But if I'm doing an infinite amount and I'm trying to find the volume of the solid, aren't I just going to integrate it and add my dx? So really I'm just integrating the area of a triangle. Okay, that's kind of what we're doing today. We are finding the volume of any shape with any shaped cross-section, any type of slice that I can make by using this. So we're integrating with our limits from a to b, and this a of x just really represents the area of my cross-section, the area of my shape. Okay, so if it is a circle, you do your pi r squared. If it is a triangle, you do your base times height divided by 2. If it is a square, you can do your x squared, and so on. Okay, let's use this and do some examples. So here's example number 1. Find the volume of the solid shown. The base of the solid is the region bounded by the lines y equals 1 minus x over 2, y equals negative 1 plus x over 2, and x equals 0. Okay, so what I suggest you do is draw a picture. Okay, the first two are just lines, this one being a y-intercept up at positive 1 and a negative 1/2 slope, right? Can I take this equation and change this into y equals negative 1/2 x plus 1? So I have a y-intercept of 1 and a slope of negative 1/2, and so that's where they got this picture right there. Okay, this one being another line with a y-intercept now down at negative 1 with a slope of positive 1/2. So that's where they got this line. Okay, this is going to help me find my limits of integration. right? Because I want to integrate from where they intersect. Okay, so if you can't tell by looking at the picture, or if they don't give you a picture, what you can do is set them equal to each other like we've done in the past. Don't forget about this x equals 0 line. Doesn't that line go like this? So that's where I'm finding this area in between here, right? All right, let's set our two functions equal to each other. I have my 1 minus x over 2 is equal to negative 1 plus x over 2. And can I solve for x? Can I solve for x first by multiplying everything by 2 to get rid of those denominators? Giving me a 2 minus x equal to negative 2 plus x. Can I move my x's over to one side, move my 2's over to one side, and get x equals 2x equals 4, so x equals 2. And so I know that these two intersect at x equals 2, which is what the picture shows. They also are cut off by this line x equals 0. So I know my limits of integration then are going to be from 0 to 2. Okay? All right. But I'm not revolving it anymore. I know though that if I were to take this picture and make it into a three-dimensional solid, kind of like the picture right up above it, okay, if I extend it up into a shape, like if you're taking a mold of like clay or something like that, and you were to shape it into a three-dimensional picture, and then you were to slice it, these little slices are perpendicular to the x-axis. So if I'm perpendicular to the x-axis, I know I'm doing it with respect to x, dx's. And those cross sections aren't circles anymore, but they're equilateral triangles. Okay, so if you look at this picture, I've taken my two lines and I've shaped it up into a kind of like a triangular, like a pyramid type of shape, so that when I slice it, I end up getting little triangle slices. Okay, so off to the side, let's talk about what those little triangle slices look like. Because if I want to find the volume of this solid, I need to integrate from, what were the limits again, 0 to 2? And I need to figure out what the area of my shape is, the area of my little cross sections with respect to x. Okay? So what is the shape of my little cross sections? Because that's going to help me get my area. Right? So I need to figure out what the shape is first so I can figure out what the area is. Well, it says here that they're equilateral triangles. So how do I find the area of a triangle? Don't I do 1/2 base times height, or base times height divided by 2? Either way. Okay, so this is what we need to fill out. We need to figure out what our base is, what our height is, so that we can plug it into this formula here. Okay? All right, let's keep going. Let's talk about what that triangle is and how to find its base and its height. Okay, oops, I'm going to draw a bigger triangle here off to the side. And this is an equilateral triangle, right? That's what it says in the problem. So I know that all the sides are the same. If all the sides are the same, I know that all the angles are the same. So aren't each of these angles 60? And I need to figure out what the height of this triangle is, what the base of the triangle is, so I can do base times height divided by 2. Okay, so this bottom, let's call this base B. If I draw down this altitude, I end up making a right triangle, and I end up making a special right triangle, a 30, 60, 90 triangle. When I do that, because it's an equilateral triangle, when I drop down my altitude, I know that I cut this base in half. So can I call this little piece right here b over 2? Because isn't that half of the base? And if you remember back from geometry to your special right triangle formulas, across from your 30 is x, across from your 90 is 2x, and across from your 60 is x rad 3. So in this case, that means x equals b over 2. So then my height would be x times rad 3, or b over 2 times rad 3, b over 2 times rad 3, or rad 3b over 2. Does that work? Okay, so if I wanted to do the area of this little triangle, I would do 1/2 times my base times my height, which was my rad 3b over 2. A more simplified version, if I were to combine my like terms, could I say rad 3 over 4 times b squared? and that would be my area of my triangle, rad 3 over 4 times b squared. Okay, so if I'm using this to integrate, then I need to take, let's go back to blue here, I need to integrate, what did we say, from 0 to 2 of the area of my triangle, rad 3 over 4 base squared dx. However, we can't do that because we have too many variables. We've got x's, and then all of a sudden we have this b in here. So what we have to do now is figure out what the base really is. What is it in terms of x's? Okay, so I'm going to go ahead and erase all of this stuff. So we can go back here. All right, so we've got to figure out what our base is. Well, if you look at your base in this picture, the base of your triangle is here. And it's in between this line and this line. Well, isn't this line here f of x? And isn't this line here g of x? So how would I find the distance in between those two lines, aka the base of my equilateral triangle? Can I subtract the two functions to find the distance between them? Right, the difference between them? So can I say that my base of my triangle is f of x minus g of x? Okay. It really helps though to have a picture. So if they don't give you a picture, I highly suggest you draw one and you visualize what's going on so you can figure out what your base is. When I combine like terms here, I've got a 2, what's a negative 1/2 and a negative 1/2? Isn't that negative 2/2, so negative 1? And so the base of my triangle ends up being 2 minus x. So can I use that now to plug it into my integration formula? Okay, I'm going to go ahead and let's see if I have any, I'm going to go ahead and erase this. All right, so let's go back to integrating. I'm going to integrate, we said from 0 to 2 of the area of my triangle, which was the rad 3 over 4 times my base squared, wasn't it? But what was my base? 2 minus x squared dx. So this is the area of my triangle. There's a whole bunch of them. That's where my dx comes from, and we're integrating it from 0 to 2. Okay, can I take this rad 3 over 4 outside of my integral? It's just a number, isn't it? Can I FOIL this 2 minus x squared, make this a 4 minus 4x plus x squared dx? Then can I integrate here and say 4x minus 4x squared over 2 plus x cubed over 3, and I'm integrating it from 0 to 2. Don't forget about your rad 3 over 4 out in front. Okay, when I plug in my 2 to evaluate, I get 8. I get 16 over 2, isn't that a negative 8? If I plug in a 2 here, I have 8 over 3. Minus, if I plug in my 0, I have 0, 0, 0, 0, 0, 0's all around, right? Don't forget about your rad 3 over 4 in front. Inside here, this positive 8 and negative 8 go away, so I'm just left with an 8/3. So on the top I have 8 rad 3, on the bottom I have 12. Outside numbers can reduce with other outside numbers. What number goes into 8 and 12? Doesn't 4 go into both of those? So I can reduce them by 4. 4 goes into here 2, 4 goes into here 3. So I end up getting that the volume of this little shape that has equilateral triangle cross sections is 2 rad 3 over 3. If you were to put that in your calculator, you would get 1.155. Okay? All right, let's do another one. So that one was one with an equilateral triangle cross section. Let's do one that has a different shape. Here's example number 2. Find the volume of a solid with go. Find the volume of a solid with base bounded by the curves of y equals x squared and y equals 8 minus x squared with cross sections that are perpendicular to the x-axis. So if I'm perpendicular to the x-axis, again I want to do it with respect to x. We're going to do dx's. We're going to have x limits. But this time my cross sections are what shape? It looks like this time they're semicircles. So if I want to find the area, the volume of this solid, I want to integrate the area of my shape. My shape is what kind of shape again? Isn't it a semicircle? Right? With respect to x. Okay, so let's figure out how we're going to find the area of a semicircle. Well, don't we know how to find the area of a whole circle? Isn't a whole circle pi r squared? So then if it's a semicircle, what does that mean? Doesn't it mean it's just half of that? So can I take this and divide it by 2 or multiply it by 1/2? Okay, so I need to figure out what my radius is, because I have a pi over 2. Isn't that just a number that I can take out? So now I've got to figure out what my radius is. Let's go ahead and draw a picture to help us kind of visualize so we can plug this into our formula. Okay? All right. Okay, so if I were to draw a picture, the first equation is a y equals x squared. That's a parabola starting at 0, then going from 1 to 1, and kind of looking like that. Maybe a little bit lopsided, but that's okay. This second equation is a parabola opening up at 8, well, way up here, and then going down, isn't it? So kind of look like that. Right, essentially. And so what we're doing is we're finding the little area. Let's do maybe a green. We're finding the little area in there. And if we were to take a little clay mold and mold it up into kind of like a little dome shape, right? Into a little dome shape. So that way when I slice this, I'm slicing into like a little semicircle, right? So my little shapes are little semicircle slices. All right. I guess I should do my slices the other way because aren't I perpendicular to the x-axis? So shouldn't my slices go this way and they're little circles like that, semicircles like that? There we go. So perpendicular to the x-axis would be little circles like that. Still kind of a little dome shape, but they're semicircles that are perpendicular to the x-axis. Okay. So we said we needed to integrate it, but we've got to figure out our limits of integration, and we've got to figure out limits of integration with respect to x since we're doing it perpendicular to the x-axis, right? So how am I going to figure out where they meet here and here? All right, isn't that the two intersection points of the two equations? So can I set them equal to each other? Can I do x squared is equal to 8 minus x squared? Add my x squared over. I get a 2x squared equal to 8, divide by 2, square root, and I get x equals plus or minus 2. So those are going to be my limits of integration, aren't they? I'm going to go from -2 to +2 on the x. Okay, so here we go. I'm integrating from -2 to 2. We said it was pi. Can we bring this pi over 2 out here? And we just have to figure out what the radius is, right? We've got to figure out what our radius is of our little semicircle. Okay, looking at our picture again, here's our little semicircle, and it kind of shoots out like this, three-dimensional, and so it kind of looks like this. So can we find the diameter of this circle all the way across? The diameter is the distance from the top here to the bottom here. So how do I find the distance from the top to the bottom, or the diameter of this semicircle? Can I do my top function minus my bottom function? What was this top function? Wasn't that the 8 minus x squared minus my bottom function, which was my x squared? So this is going to give me my diameter of my semicircle. And so I end up getting 8 minus 2x squared. But I don't want the diameter, right? Don't I want the radius? So if this is my diameter, how would I get the radius? Could I cut it in half, divided by 2? So that means the radius of my little semicircle is going to be 4 minus x squared. Can I plug that into my equation? All right, let's integrate it. Here we go. I'm probably going to FOIL this out before I integrate it. I have pi over 2 from negative 2 to 2 of 16 minus 8x squared plus x to the 4th. Okay, I'm going to integrate. I have 16x minus 8x cubed over 3 plus x to the 5th over 5. I'm integrating from negative 2 to 2, and don't forget about your pi over 2 in the front. There we go. If I plug in a 2, I end up with a 32 minus 2 cubed is 8, 8 times 8 is 64, so what's that, 64 over 3, plus if I plug in a 2, 2 to the 5th power is 32 over 5, minus, if I plug in a negative 2, I get a negative 32, I get a negative 8, and then negative 8 is a positive, right? 64 over 3. If I plug in a negative 2, I get a negative 32 over 5. Don't forget about your pi over 2 in the front. You could sit here for a while and get a common denominator, get me an exact answer, or you could plug it in your calculator and get me 53.617. 53.617 would be the area of this solid if the cross-section was a semicircle. Okay? So, anytime I ask you for the area, and if the cross-section is not a circle, or is not a disc, or is not a washer, you just got to integrate what the area is, depending on whatever the shape is. Triangle, circle, semicircle, square, whatever it might be. Okay? All right, your homework is 7.2b. You're doing page 463. Remember, you're doing numbers 1 through 10 on the calculator. Just set me up an integral and evaluate it in your calculator. You're doing numbers 52. You're doing numbers 61 through 63, but you can skip 63 part D. I'd like you to do the other parts, but you can skip 63 part D. I'll see you tomorrow.